In this video, we're going to introduce implicit differentiation. And to illustrate this idea, we're going to first consider the equation of a circle of radius 2, x squared plus y squared equals 4. Now, before we go into implicit differentiation, one thing I want to emphasize is that this is simply an application of the chain rule, which we've already seen. And now we can see this derivative, what it's supposed to look like, if we consider our circle and we draw a line. We pick any point x, y on the circle, and we draw a line from the origin out through that point x comma y. And the slope of this line, this blue line, is just simply rise over run, or y over x. That's the slope of this blue line. And if you remember from algebra, the slope of a line perpendicular slope is simply the negative reciprocal. So this tangent line to the circle is also perpendicular to this blue line. So this red tangent line to the circle is going to have a negative reciprocal of our blue line. So it's negative x over y. So this red line is going to be our tangent line to the circle at xy. Another way to say that is, this should be the slope of our tangent line when we apply implicit differentiation over here. So let's see if that actually comes up that way. So now, in order to differentiate, first thing we're going to do is we're going to differentiate with respect to x. So we're going to apply dx, both sides. We're taking the derivative of the left side of the equation with respect to x, as well as the right side with respect to x. Okay, now, if we apply the derivative with respect to x of each of the terms on the left side, we'll have dx. I'll do all the light blues first. dx and dx. So the derivative with respect to x of x squared, and then the derivative with respect to x of y squared, and the derivative with respect to x of 4. So now the derivative with respect to x of x squared is the usual power rule. That's just 2x. Now here comes the fun part. The derivative with respect to x of y squared, this is where we're going to require the chain rule. So if you're trying to figure out, well, when will you know if this chain rule idea is going to pop up? Usually it pops up when we're differentiating one variable with respect to another variable. So you see that the y doesn't match up with the x. So this y we're going to need to think of in terms of some function of x. So remember that the chain rule tells us that dx of y squared is the derivative of y squared with respect to y times dy dx. Now if we were, although we're not going to, if we were to cancel out the dy's, we'd end up with dy squared over dx, which is dy squared over dx. That's what we started with. We don't cancel out the dy's. We actually want to see this chain rule written out explicitly. So let's remind ourselves that this is the chain rule being applied. And so the derivative of y squared with respect to y, that's the usual derivative. That's just 2y. And there's nothing else we can do to simplify dy dx any further. And so this is the derivative of y squared with respect to x. So here we have 2y times dy dx. And this is our derivative of y squared with respect to x. And then the derivative of 4 with respect to x, there's no change occurring with respect to x. The derivative of a constant is simply 0. So we have 2x plus 2y dy dx equals 0. And all we really want to do here is solve for dy dx. Just like we would in algebra, our unknown or our term we want to isolate is dy dx. And so we have 2y times dy dx. I'm going to subtract 2x from both sides. And 0 minus 2x equals minus 2x. And again, we want to isolate dy dx. So we're going to divide both sides by 2y. The 2y's cancel. Over here on the right, the 2's cancel. And we're left with dy dx equals negative x over y, which is precisely what we had hoped for with the slope of the tangent line, or the slope of the perpendicular, right here, the negative x over y, so that we have a match. So geometrically, we showed ourselves that the slope of the tangent line to any point x comma y on the circle is actually negative x over y. We used calculus, or implicit differentiation, to show that the derivative of the equation for our circle with respect to x is actually negative x over y, which tells us the slope of any line at x comma y on a circle is going to have negative x over y slope. So let's take a look at one quick example, or another example, say. The derivative of y with respect to x, or the dy dx, for the equation x squared plus y squared equals 3x to the fourth plus 2y cubed plus equals 1. So we apply the d dx to both sides. D dx. I'll just run through this example since we've seen already how this works. We have on the left side x squared y squared plus 3x to the fourth plus 2y cubed. On the right we have 1. So here we have the derivative of x squared y squared with respect to x. So again, let's start with the light blue. D dx. And I'll separate each term. And I'm taking the derivative with respect to x of each of these. Okay, so x squared y squared. And then here we have 3x to the fourth. And here we have 2y to the third power. And on the right-hand side we have 1. So the right-hand side, that's the easy part. The derivative of 1 with respect to x is 0. The derivative of any constant with respect to x is 0. Okay, now here, the derivative of x squared y squared with respect to x is the product rule. So we're going to take the derivative of the first term, that's 2x, times the second term left alone, plus the derivative of the second term, which is the chain rule, that's 2y times dy dx, times the first one left alone. So this was the product rule, where we took the derivative of the second term, that's 2y times dy dx, and then the first term was just x squared left alone. This is not quite as tricky. It's just the derivative in the usual way, 12x to the third, and d dx of 2y cubed. At the chain rule, that's going to be 6y squared times dy dx. Okay, and now we want to isolate those terms that have dy dx in them. We want to keep those together on the left side. Everything else will go over to the right hand side. So we have 2y x squared dy dx plus 6y squared dy dx equals, now I'm going to group the 12x cubed and the 2xy squared, and I'm subtracting both of those as a group over, so I have 2x negative in front, 2xy squared plus 12x cubed, and now I want to factor out the dy dx. There's a common factor of dy dx in each, so I have 2yx squared plus 6y squared dy dx equals negative 2xy squared plus 12x to the third power. Now to solve for dy dx, we will divide both sides by 2yx squared plus 6y squared. Do that on the right as well. 2yx squared plus 6y squared. So these will cancel, and I'm left with dy dx equals this expression, which is a pretty sophisticated derivative. Okay, so I hope this gives you a little insight into when implicit differentiation comes up and an example or two of how to compute the derivative implicitly given an equation.